Good evening, everyone. Welcome to Kinetic Space Above and Beyond, which is the second lecture from the Royal Aeronautical Society Boscombe Down branch this year. My name is Jeff Clarkson. I'm the Vice Chair of the branch, and I wish you a warm welcome to our lecture this evening. In a bit, I'll introduce Stijn Ilsen, who's going to be giving the lecture. So he's a 40-year-old aerospace engineer, and he joined Kinetic about 15 years ago. And he works on in Belgium, which is where most of our space work continues in the Kinetic business. He started as a test engineer on a satellite project called Proba 2, and I expect he will explain a bit more about that. Tested the full satellite, part of the launch team, handover process of the satellite to the customer. And after that, he moved to being a systems engineer on the Proba 5 satellite. And he's now also involved in all Kinetic satellite projects as a senior satellite operations engineer. And in the free time, he writes children's books about space. I'm sure Stijn will be happy to answer questions about his book as well as space. So without more ado, we'll just switch across to his presentation, and I look forward to your talk.
Good evening, everybody. I will try to entertain you for 45 minutes about Kinetic Space and our activities above the clouds. Okay, let's give it a go. So let's start with first explaining what Kinetic Space actually is. So Kinetic is a very big group, as you're aware. Kinetic Space is only a very small part of that. We were founded about 50 years ago in Belgium, in Kruibeke, which is very close to Antwerp. We currently have about 200 employees, of which I think in the last year only 50 people joined. So we are currently more or less exploding, which brings its own challenges. But okay, it's definitely very amazing right now. We have 3 sites under our responsibility. We have the site in Kruibeke, where we build satellites. We have the site in Urdu, where we operate our satellites, and we have also a piece of the site of Farnborough, where the UK part of Kinetic building space is also actually under the Kinetic Space branch. Actually, the company was not started as Kinetic. We were bought by Kinetic. I'll give a bit more of the history in the next slide. We became part of Kinetic Group in 2005, and within Belgium we are the most experienced satellite provider. There's only one other provider which provides these CubeSats, but for actual satellites you need to come to Kinetic Space. History, yeah, Mr. Verhaert, our godfather, he started the company in 1996 doing industrial design. He's a very famous Belgian designer. He wrote some books and gave some lectures. And since he was with his company always building prototypes, he thought, okay, building a prototype for a company is more or less the same thing as building something for space. It's also always a prototype. You always build a one-off. So in '83, he started with space activities, and then in 2001 we launched the first satellite, which is Proba 1. In 2005, then Kinetic Group bought Verhaert, and then we changed our name to Kinetic Space in 2010. Our portfolio of products, I'm going to hang it up a bit at different topics. So we start with Proba, which is our satellite business. Then we're going to move to docking systems. We have some life support, which is more astronaut related. And then there is some bits and pieces of a bit of everything, which is then and beyond. We'll see how we get there. But let's start with the beginning. Proba is our satellite platform. Proba stands for a project for onboard autonomy. They're what they call small satellites, 100 to 150 kilograms heavy. We're moving now more into the 200, 300 kilograms category. And the fact that we have onboard autonomy in our name is one thing which we do different than other people, at least in the past. We were from the beginning, and Proba 1 was launched in 2001. We were one of the first companies who built satellites which actually had to take care of their own. And the team on the ground is therefore very, very small. And for Belgium being a small country and Proba 1 being paid by the Belgian government, this was very important. So we were obliged to apply autonomy to save on operational costs. And eventually it became more strength in the market because we were the first one to actually have autonomous satellites. But let's start with Proba 1. It was the first Belgian satellite launched in October 2001. I was not there at that time, but my colleagues who were there, they explained to me many times that they would be very, very happy if it would have survived a week, a month, maybe half a year. They would be really, really happy, although the requirement was to have it at least for a year. But there was the first satellite in Belgium, the first satellite built by ESA with a very small budget. So everybody is extremely happy that even today, after more than 21 years, the satellite is actually still in orbit and still performing very well. Of course, technology has evolved, so our cameras are getting a bit old, and the memory is completely not comparable to modern day memories, but it's still fully operational. One of the nice things which was done from the beginning is that we make it safe. There's no deployable panel, as you can see, just a big box with solar panels on all sides, meaning that it's impossible to break. We cannot break the satellite. So even though it was built for 1 year, our customer is never asked to build another one, because after 20 years, it's still fully working. These are the pictures which we take with Proba-1. We are specialized in small little islands, which big satellites usually skip, atolls, stuff like that. And we're also specialized in disasters. The main reason being that Proba-1 is a very agile platform, so we can point the attitude, or we can change the attitude quite fast. And we only have a single scientific user, which is actually located in SSTL in the UK. And since you have a single user, the single user can decide to do retasking very, very fast. While if you have a very big satellite with 20 plus cameras, or 5 cameras, whatever, then you need to go through a whole sequence of loops in order to change the science planning. So in this case, we can just point it to an area where, for example, a volcano erupted or a flood was happening, and we can take hyperspectral pictures, so in many different wavelengths. Then Proba-2 came, 2009. Proba-2 is a space weather satellite. So it's taking images of the sun. It has also 17 experiments on board. Typically in space, if you would decide to launch your own space company and you have a good idea of a new battery, for example, nobody will buy your battery because it's not space qualified. People with big budgets, with mature satellite designs, they're only buying stuff which has already flown before, or which is a small adaptation to that previous design. So with Proba-2, we decided to go into the route where we offer the opportunity to a lot of companies within Europe to fly a new technology, which we don't need to sustain the satellite, but which you can test in orbit, and then basically the company can get some kind of flight diploma to show that their experiment or their technology has been flown in space. It's fully autonomous, meaning we have basically no operators there to operate it. The science users can send the request over the internet. It arrives in the RAeS site, it's being uplinked, and the same day the new pictures are downloaded. So it's a very nice satellite. 2009, built for 2 years, and also still fully operational. The nice thing about Proba-2 is that it makes these nice videos. I hope this will work through the Teams and for the people which are watching on the other link. So what you see here is a picture of the sun every minute, sorry. And yeah, basically I was a bit disappointed because after 10 pictures as a satellite operator, I more or less saw that the sun was in the middle, and I was very happy. But for the science people, this is always very, very nice, and they want to see the flames and the eruptions and the solar spots. But then at some point on June the 6th, 2012, something interesting happened for me as well. And we see there a planet passing through the sun and the Earth, and the planet is Venus. This is a Venus passing or a Venus crossing. Don't know what the exact wording is. So Venus passes in between the sun and the Earth. And as you might have seen, Venus is going up and down. If this would be an interactive session, I would ask you, why is Venus going up and down? But I'll now just explain it. Of course, Venus is not going up and down, nor is the sun. So it is actually the satellite, which is orbiting the Earth in a polar orbit. So it's going from North Pole to South Pole, what we call a 6 o'clock orbit. So it's flying always over the dusk dawn line on the Earth. And that's why it's never in eclipse. It's never behind the Earth with respect to the sun, but it of course flies up and down, and therefore you see Venus a bit from the top and then a bit from the bottom, and it looks like Venus is moving, but in fact it's the satellite which is Then our last satellite which we've launched is actually Proba-V. There was a Proba-3, which is actually still in our clean room. There was a massive reassessment of the goal. I will talk a bit about it later. Proba-V was an interplanetary mission, which was cut for budget reasons. And then Proba-5 or Proba-V for vegetation is a mission which studies the vegetation on the Earth. The nice thing about Proba-V is that I got to do the whole test campaign from the beginning to the end, design, testing, launch, operations. It's one of the nice things about working at Kinetic compared to, for example, building a satellite at Airbus. In Airbus, they have a team doing feasibility studies, they have a team doing preliminary design, a team doing testing of the flight equipment, a team doing launch. At Kinetic, we're much smaller, so we have one team doing the entire thing. You get to be confronted with your own mistakes at the end. If you made mistakes in the design, it's a really nice environment to work in. As you can see, the team is not very big. We usually have about 10 people working on a single satellite. We built different models. STM is a structural thermal model. Then we build an EQM, which is an electrical or a qualification model. And then we have a PFM, which is a proto-flight model. If you would build proto-flight models a couple of times, then you just get flight models. We're working in a clean room, as you can see, and we do a lot of testing. Basically, I think typical duration of a satellite project is probably 5 years to get the funding right. So that's more the worry of the scientist, which needs to convince people to provide the right funding. And then as soon as we come in the picture, it takes about 3 to 4 years. 1 year for design, preliminary design, let's say, 1 year for the critical design review, and then 1.5 years of testing, and then launch and commissioning, and then you're more or less 4 years away. This is Proba-V when it was done, and I'm showing it in my full dressed up clean room suit because it was an optical satellite, so we had to be very, very careful about cleanliness. We test a lot. This is a satellite being hang in a thermal vacuum chamber. Of course, the satellite is normally always tested in a clean room, but in a clean room, testing your satellite thermally is very difficult because there is air, so the heat dissipates through the air, while in vacuum the heat needs to be distributed through radiation or through conduction. So that's why we do a lot of thermal vacuum testing. This is typically done in Toulouse. We also test the satellite on a shaker. So one of the worst things which could happen is that the satellite doesn't survive the launch and that something breaks. And to test that, we actually put it on the shaker. And in many cases, not too many in our cases, luckily, but in many cases, these reveal structural issues because, of course, a satellite is built for the lowest mass possible. So yeah, if you lower the mass, then the margins go down, and if somewhere there's a peak in the stress, then you will see that something breaks. And then we are ready to pack. Satellite is not too big, so we don't need a very big container. We have just a special container to fly to Kourou. Why do we fly to Kourou? Well, all European launchers are currently launching from Kourou. There are some new launchers launching from the Scandinavian, and there's also a UK endeavor to launch from the UK. And of course, there's Virgin launching from a plane. But currently, the biggest satellite, the biggest rockets are launching from Kourou. Kourou is in French Guiana. It's a part of French overseas territory. It's still France, so you pay with the euro. They speak French, and you can only rent a Renault, a Citroën, or a Peugeot. So it feels very French. And if you fly from Paris, it's even an interior flight. I don't know the exact wording. So it's really a very special area in the world. And of course, they launch from there because it's exactly on the equator. The Americans don't have anything there, but they launch from the south of Florida to get as close to the equator as possible. Well, Europe has this former colony there, which we use to launch the European launchers. Proba-V was launched on Vega, and then if I tell this to some people, then it must be a big rocket, but no, Vega is a very, very small rocket. It's at the top of your slide. It's specifically built to launch small satellites up to about a ton into LEO. LEO is low Earth orbit, so about 700-800 kilometers high. So compared to Ariane 5, for example, compared to Falcon 9, this is not a very massive rocket. and Vega is also mainly built by the Italians. But it's a very performant rocket, although the last couple of launches, I think it had 2 failures. So they need to work on some reliability issues. Then just walking through a bit of a launch campaign. I didn't really know exactly who was going to dial into this meeting, so I thought let's not make it too technical. So also a little bit of experience. This is my photo collection of the launch campaign. If you ever go to Kourou, try to stay in the Hotel Les Roches on your right. The other hotels are basically not good, and it's on the equator, so there are a lot of crawling animals there. So if you want to have a good, safe, nice hotel, then stay in Hotel Les Roches. You get to Kourou on a big road. This is the road, the national road of French Guiana, the N1, from Cayenne, the capital of French Guiana, to Kourou. It's about 1 hour drive or 2 hour drive, if I remember well. When you arrive in the Kourou Space Center, then you immediately know that you're on the right place, because there's a huge Ariane 5 rocket on the parking lot. You can see, for example, that they have quite some administration buildings, but in the back you also see clean rooms. They have different types of clean room for different types of activities. This is these Ariane 5 rockets at I think it's scale 1:1. So the first thing we do when we get to Kourou is to unpack the satellite from the container and to do a health check, see whether everything still works fine. Of course, it's built to sustain a rocket launch, so it should be able to handle a flight with an aircraft. But still, it's important to check that everything is still working fine. And after that, we put it on top of the very top piece of the rocket. So the thing you see on your left is actually the top of the Vega rocket. The rocket is built both from the bottom up, but also from the top down. So we hang some pieces also on top of on the satellite. Basically, this is our interface ring and the deployment mechanism. This is our team in Kourou. I'm the one on the right, second one from the right. I was a test engineer, system engineer at that time. We were very proud to be in Kourou, and it's you're away from the family for 2 months, which is of course a bit of a challenge, but it's also nice. It's really what a team is built for. You test for years at a time in your own facilities, and then it's a bit like the Olympics. We're usually not the most sportive people, but we do get our own Olympics, so we can get to go to a launch campaign, perform well, and get the satellite into space. I was in Kourou actually already a couple of years ago with when I was working for Airbus, and this is a European scale project. So this is about a satellite. This is called Herschel. It's a space telescope. The total budget of Herschel was 1.1 billion euro. So it's a huge project. While if you would talk about a typical probe satellite, you're talking about 50 to 80 million. So it's a very different scale, and with bigger price comes also a massive amount of people which want to join the launch campaign. To give you an idea, all the people in blue are people from ESA. They are our customer. They're only there to ensure that the people not wearing blue are doing a proper job. So there are a lot of people watching our hands and watching our activities in Kourou. Then while we are doing all the testing on the satellites, the people from the launcher are building and integrating the launcher. This is the Vega rocket. It has, I think, 4 stages. So the stages are put on top of each other one by one. The rocket is actually assembled in a special building for that. And this is a funny story, when you escape from the building, or when there would be a fire in the building, so typically we work in this building like 30, 40 meters at one of the highest floors. If there's a fire in the building, then yeah, you're standing next to a rocket with over 100 tons of highly explosive material. So there must be a way to get out safely. In the SpaceX world and in the NASA world, there's usually a detrite system where you hook yourself to a detrite and you slide away from the building one after the other very fast. The French wanted to do it differently, so they built a very special system, which is the following: you basically jump into a hole in the floor, 30 meters above the ground, and you're falling basically to the ground floor, but you're more or less, there's some kind of break because you fall into Yeah, I don't know the English word, but you fall into like a net, a very fine-maced net, and there's a hole in the net at the bottom, and then you fall from one net into the other one. At some point, you sometimes fall 2 meters where there's no net because there's an entry for other floors to jump into the same hole. Being an engineer, I never understood why this is an efficient way, because if you get down, you're basically still extremely close to the rocket because you just vertically went down, and usually you're not the only one working at 35 meters above the floor, and usually my colleagues are bigger and stronger and way more than myself, so I'm not going to be the first one jumping in this hole and then having all my other colleagues landing on me. But anyway, you have to try this, otherwise you don't get your safety approval. So we do that, we try it, and then we get our badge and we can finally get to work. This is one of the last pictures we have of Proba V. It was actually the second launch of Vega, which we had. The first launch was a test launch where there were actually no satellites inside. Typically, a Vega launch is something we cannot pay for. I think it's like 15 million euros to get to the primary passenger position. So typically we're in the bottom. Actually, we're normally within the pot, the cylinder which you see, but because it was a second launch, we got the launch for a massive discount. Well, ESA actually arranged the launch, and we were primary passenger at the top of the rocket. So it was a bit of a risk as well, because of course the second launch is not always the most reliable one. Then, so we're put in this enclosure, which is what we call the fairing, which is the top of the rocket, and then we get hover. Yeah, we put on a crane, and then they put all the pieces of the rocket together. So our satellite is in here, and then everything is integrated, and then the rocket is ready. Instead of rolling the rocket away from the building, this works differently. Again, engineering-wise, for me, it's sometimes difficult to understand, but they decided to actually roll the building backwards instead of rolling the rocket forwards. And of course, rolling a big building backwards, it's not easy. So we got a delay of a couple of days because the rolling mechanism was broken on our rocket launch. Just one minor touristic tip: if you would be in Kourou at some time and you want to see a rocket launch, go on the beach or climb Monkey Mountain. Monkey Mountain is a mountain which is next to the launch facility. So you basically have the ocean, you have a beach, then you have the launch facilities, and then you have a mountain, which is Monkey Mountain. It's about a 3-hour climb in tropical temperatures. You're in the middle of the tropical forest. There's some monkeys there, and there are a huge amount of other creatures which are crawling and flying and biting and stuff. But if you don't take a guide with you on that climb, then you don't see any of these creatures. It's only when you take a guide that you notice them. Otherwise, you can just easily walk up and down. But the view from that mountain is amazing. Also, the rocket is going away from you, launching over the ocean. So you have the noise and the vibration standing on that mountain. So we were lucky with one of the launches which I had in Kourou, that I was there for a previous launch on which I had nothing to do. So I was a tourist, a visitor, and we climbed the mountain. It was really nice. So just if you're ever there, then have a look. What does Proba V do? Let's switch to the next one. So my task was satellite operator for the launch. So I'm sitting here in front of my control center. As you can see, a launch attracts a lot of very important people. I was flown from Kourou to Belgium again a week before the launch because I was needed for the first contacts, but there are some people from our team remaining in Kourou. The nice thing about Proba satellites is that they're actually off during the launch, so we have nothing to do. We have a go, no go button, but the only thing we need to check is the battery. We have a wire running all the way through the rocket to be able to check the battery, and then it's like in the movies, you have a roll call, ready for launch, yes, and then they ask primary passenger ready for launch. You say yes or go, and then they're launching. I was part of the LEOP team. LEOP is Launch and Early Operations team. We have a lot of fun doing rehearsals in the middle of the night and making sure everything is ready. And we have contact with all the ground stations around the world which support us. And then we have the launch. I don't know whether you can hear the sound actually, but anyway, it's some It's a French lady counting down. For some reason, all our launches have been happening with extremely poor weather, which means that we never have good footage of our launch. As you will see, after more or less 3 seconds now, the rocket disappears into the clouds, and we have no visibility, no nice movies to show to our customers, except for this this nice rendering. But of course, this is not what you want to see. But that's what you have if you launch from the equator. These are the pictures. No, this is the first signal. It's really nice. We have an antenna here in Australia. So the rocket launches from Kourou, South America, over Africa, Australia, and we are separated from the launcher above Australia. And there we had an antenna, and you could see that that light boots up. If you see a signal like that, you know it's separated from the rocket. It has activated the satellite itself, and the transmitter is working fine. So really nice. Yeah, we were all very happy. We had a party, but basically our work only started because we were the launch team, so we had to make sure that everything was done properly. As you can see again, we have 2 operators from Kinetic, and we have 1, 2, 3, 4 people from ESA, which are checking what we're doing. In the end, they're the end customer. They're paying for this satellite with taxpayers' money, but anyway, they're responsible. So they're looking carefully to what we do. How do we do operations? This is the Kinetic Center in Redu. So we have a lot of dishes there. It's not only Kinetic; it's actually owned by ESA, but Kinetic has the right to facilitate the site. I don't know the right English word for that. We do that together with SCS Astra from Luxembourg. We have about 12 minutes per contact. So when the satellite passes over Redu, we see it for about 12 minutes. It's traveling at 7 kilometers per second, so it's going really, really fast. And we only have about 3 contacts per day, so about half an hour of contact time. But we do have other contacts above Kiruna, which is really in the north, where we can dump some science data. And since our satellites are highly autonomous, we have 6 people to operate the three satellites. So it's really, really minor. Well, a very, very small team. Compared to a normal ESA satellite, you normally have about 12 people working in shifts. We have 6 people for 3 satellites. And this is how the satellite orbits the Earth. So as you can see, you're not seeing Belgium on these orbits. Maybe now you see it on the backside, but we have normally 2 contacts in the morning and 2 contacts in the evening. And these are the pictures which we take. So every day we take a picture of the full Earth in different frequencies, and then we can monitor the vegetation. Much nicer to look at than the sun weather observations of the sun. Here you can actually see a lot of changes in nature, and our data is used by I think 46,000 scientists all over the world to investigate sometimes a very small piece like a forest in the UK, but sometimes people investigate the full Sahara desert to see where the desert forming is slowing down or where it's increasing. This was a bit about our satellites. I will talk a bit at the end on what we plan to do next. But we also do docking systems. Now, what is a docking system? Docking system is the thing you see at the back of this space shuttle-like vehicle. It's basically an interface ring, which is on both sides of 2 vehicles, and it allows to dock 2 vehicles in space. It's mainly used for manned spaceflight, so it's sized such that a person can fly or can slide through it. The applications for docking systems are quite wide. We can use it not only this one. We can use it for docking with manned spacecraft, but we also have a branch within Kinetic which is using docking technology more for orbit, for orbital debris removal. This is an animation from a study phase we did to capture MVSat. MVSat is a satellite built by the European Space Agency a long time ago. It has a lot of experiments. I think the total size is about 12 meters. And the solar panel is another 10-12 meters. Kinetic actually built part of this. One of the booms, I think it's on the other side, this antenna boom, which you see on your right, is built by Kinetic. But it has become a piece of debris because in I don't remember exactly, but 2015 or so, ESA lost all communications with this massive satellite. It became then one of the biggest pieces of debris which is currently orbiting the Earth. And there's just a statistical chance of about 100% that it will at some point collide with something else, just because of the size and because of the fact that it remains in orbit for at least another 150 years, because the natural decay for such a heavy orbit, heavy object, is very, very, very small. So basically, this is a big risk of providing a cloud of debris, while currently it's just still one little piece. Well, one big piece, but at least it's a piece. But to get to that satellite, we need some capturing technology, which we're currently doing. So we have this robotic arm, which we are developing. And the idea would be to fly to ENVISAT to capture it and then to bring it back to the Earth. Now, in this movie, it sounds really easy. You just go there, you grab it, and then you come back. But the main problem which we have with orbital debris removal is that you want to be sure that you don't become debris yourself. And it's not the idea that your garbage truck, which comes to collect some piece of garbage, is actually colliding with your garbage and actually producing a whole cloud. So it's very, very important that you have all kinds of safety and reliability measures in place to make sure that you can capture the target well. And in the case of ENVISAT, this is extremely difficult because ENVISAT is spinning. It's spinning around its longitudinal, around the short axis, as you can see there. So you can't just go there and grab it. You have to go on the side. So you see the chaser spacecraft here. We are going with the Delta V maneuver, going on the side, and then we're slowly approaching. And then still we can't capture it because our target is moving and we are not. So we need to go into an active spin. At this point, we lose the contact with the ground because the antennas are blocking the visibility. The solar panel is blocking the visibility to the ground. So we have to do an auto rotation, which is thruster induced. And then during that rotation, we have to grab the satellite. And once we grab it, then we can stabilize it and then we can slow it down. We are currently still working on this project, although it has been postponed until new technology has been developed to do it better. Currently, the cost was about, I think, 250 million for a single garbage truck to collect a single piece of debris, knowing that there are at least 5,000 satellites in orbit which are not operating anymore. So it's the technology needs to advance further to lower the risk and to get the cost down. But our docking systems are also used for servicing. Stop the sound. We are also thinking about servicing bigger satellites. For an Israeli customer, we are developing a system where we could go to an geostationary satellite, which is typically commercial satellites, which might be out of fuel or might need some other things. And we could go there with a custom platform, we could dock to it, and then we could take over the GNC function. So the pointing, for example, we could take over. Or if the satellite is equipped for that, we could also refill the tanks. But older satellites are typically not equipped with refill valves or stuff like that. New business which we're developing. But everything started with the docking system itself, and docking is something is done every day. In the ISS, there are lots of different docking ports, but in the past, every country has its own docking system. So, sorry, needed a drink. So the Russians have a Russian docking system, the Americans have an American docking system, Europeans have a European docking system, and it went on like this, and it makes the puzzle very difficult because if you want to fly something to the ISS, you need to know beforehand what will be already docked, so which ports are open and which ones are not. Knowing space and the delays and the shifts of priority, which can happen, it's very difficult then to predict which docking port you need to mount on your spacecraft. So at some point, people thought, let's put our things together, and NASA, ESA, Roscosmos, so the Russians, JAXA is also part of Japan, decided on an international docking standard. I think it took about 20 years to get to a standard. And Kinetic is actually building the European docking system according to this standard. This docking system will be used for docking, as you can see here on the left. So docking is really an automated docking sequence. You also have berthing, berthing is actually the robotic arm will capture the spacecraft approaching the ISS with this robotic arm, and then the robotic arm will actually put that spacecraft onto a port. It's a different system, so you need also different docking rings. And IBDM is therefore our one docking ring to rule them all. So we are now compatible with American systems, Russian systems. Everybody will use the exact same system, which also makes sure that, for example, that if you would have a contingency, you need to launch something quickly, that you don't need to worry about whether your docking ring is actually fitting on your target. It's a very difficult spec'd thing, because we need to be compatible with 25-ton vehicles, but also 5-ton vehicles. So it's really a difficult thing to design and to size your motors and your dampers for. But we did a quite good job. I think what you see here is how it will look like in the end. So this is the Sierra Nevada vehicle, which is currently developed by the Sierra Nevada Corporation in the US. They've selected the European docking system, so the Kinetic docking system, because the one from, I think Boeing is building the one from the US. It's much more expensive, and it's a less performance, so it has a lower chance of docking than the Kinetic Belgium or the Kinetic Space system. Here you will see a bit how it works. So this spacecraft will be approaching it, and we are building that piece on the system on the let's say space shuttle part. It has these 3 ears which are used for auto alignment. Then there are also alignment pins, and then we have a hard docking and a soft docking with clamps and stuff like that. I'm not at all an expert on this. I'm more on the satellite side, but it works really well. The reason why we are so good is that we are docking under many different circumstances. So we have tested our system at different speeds, different angles, and we have a very, very high rate of success. Knowing that you have astronauts on board, you don't want to do docking twice or 3 times because the docking system just didn't dock. No, you need to be able to dock under nearly all circumstances, and that's where we're very good at. We also now have this robotic arm, which is also used by automotive to assemble cars, to allow us to test in our own clean room or in our own test facility these docking systems. So as you can see, even with a very high horizontal velocity, so not the velocity approaching the target, but the velocity perpendicular to that, we still have a big chance to dock. As you can see here, this is a switch from primary to redundant, so it's a fully hot redundant system. But if we switch, the system can take over. Again, for human spaceflight, this is mandatory. If we would lose power, so we cannot do an active docking, then still there's a high chance that we can do a passive docking, that the motors damp the motion by itself. Of course, you will stay connected, but you will not do a hard dock in that case. You need to restart your system. And then we also have a model. Typically in space, we do a lot of modeling because this hardware is just extremely expensive to build. It's always custom built. All these elements we need to buy specifically for us because nobody else is using them. But if you have a good model and you can correlate that model with your hardware, then you can do a lot of testing with that. And we've sold our docking system to 3 customers. One is Sierra Nevada, and the other 2 will be flying on the new space station, which will be built around the moon, on the IHAP module, and on another one, which I forgot the name. Then let's look a bit at the astronauts. So we do some life support things as well. Let's take the example of our Martian, Matt Damon. If he is on Mars, then what does he need? He needs water, he needs oxygen, he needs to exercise for his muscles, he needs food, and he needs shelter. For nearly all of these topics, Kinetic is doing something. Just to give you a bit of an overview, for example, let's start with food and water. If you go to the International Space Station, then it's a 6-hour flight. So if you want to resupply, you can just send up new water and you bring it down. It's expensive, but it's not impossible. If you go to the moon, then you can still try to take some water with you if you stay for a couple of days. But if you stay for a longer period of time, it's not possible anymore to do do resupply each time. You need to recycle. You need to turn your wastewater again into drinking water. And if you go to Mars, then there's no choice at all. You have to grow food, you have to recycle your water, you have to do everything yourself because you can't take enough food and water for the full, I think it's minimum 300 days you're out. I think it's even more than that. For exercise, what does Kinetic do? Well, we have developed a treadmill for the ISS because the astronauts need to do exercise, and this treadmill was tested in a zero-G flight. The person you see in the back is very famous in Belgium. You guys don't know him, but he's the second Belgian astronaut. We only have 2 Belgian astronauts, but he was involved in that flight because typically these things are tested before launching into the space station. We're testing it in a zero-G flight, so in a plane basically, and we take astronauts with us to make sure that they approve the design or can provide valuable inputs to our design. This was a very specific research thing. So astronauts typically can get quite sick in orbit. Their orientation system is fully disturbed. But you have some people who have no problem at all. And to do training of astronauts, we developed a chair basically, which is strange because in the ISS you don't need a chair, you're just floating away. But if you're sitting on the chair, you can do some exercises which characterize your eye-hand coordination. And that's very important because if you would have very, very bad hand-eye coordination for, let's say, the first month that you're in the ISS, and typically we're talking about weeks and months, then yeah, you're just not a good astronaut. Because you're just not very performant and you actually might break stuff. So it's important to be able to check that. So they're actually letting all the astronauts passing by our chair to do some tests, the good ones and the bad ones. And then we also have the same setup on the ground, and we will characterize what kind of things astronauts will need in order to overcome this bad hand-eye coordination. We launched it on an Antares rocket. I still remember it as if it was yesterday. I was not part of the project, but we were sitting with the people doing the project in a big meeting room at Kinetic, enjoying one of the launches of our hardware. And as the rocket goes up, we were of course all applauding, and the champagne came out. Until about 20 seconds later, when our nice Antares rocket and our chair turned into a big firework, and probably one of those pieces there is our chair. They actually found back a piece, and if you would ever visit Kinetic Space in Belgium, then like every company, there's like this glass cupboard in the entrance where we can put some things to show off to customers. One of the things which is there is a part of the chair which is on the one side is completely black because of the fire, on the other side it's still fully intact. So it's a nice thing. But we got to rebuild the chair, and this is the one which is on board. So it requires the astronaut to make certain movements in certain directions with pieces. Sometimes I think the astronauts are really doubting what they have to do, but scientists apparently can get a lot of data from these type of experiments. But we were talking about what you need on Mars. So we talked about exercise. Let's now talk about water. So this is the first Belgian astronaut, and he had a very famous talk with our prince actually, who is now the Belgian king. And it's a famous telephone conversation. In Belgium, everybody laughs with the questions which the prince asks, but I just made a new discussion on this telephone call. So the astronaut says, "Yeah, I need about 4,500 liters of water per year to just keep me alive in space." And then our prince or our king now says, "How much? That's a lot." And indeed, without recycling, this would cost about 125 million euros per year for a single astronaut. So they usually have about 6 to 10 astronauts in the ISS. And if you would extrapolate to the moon, then you're just for launching water, for a single astronaut on the moon, you need more than 1.6 billion euros a year. So we need to do something with this water. We need to recycle, and that's what Kinetic is good at. We work with algae, and we've developed a full water recycling. So on one side, you just throw in wastewater. I don't need to tell you what the wastewater will be. You can imagine that yourself. It's also captured from the air because of the astronauts which are sweating. It's being all the way fed through a system, and it's then recycled into drinking water. We have this system at Kinetic, and we also deployed it in the South Pole bases. There's a South Pole base which is operating our recycling system because they have the same kind of issues. Our astronaut, we had exercise, we had water. It also needs food and oxygen. Well, we're working on a technology which is using Spirulina, and Spirulina is what gives the blue color to Smarties. I don't know how old my audience is today, but when I was young, I remember that there were no blue Smarties because there was something wrong with the product which they made the blue with. And then for, I think it was about a year or so, there were no blue Smarties until the guys building Smarties found Spirulina. Spirulina is an algae, and if you use it it tastes very bad, by the way, but if you use it to make sweets, then it gives the blue color to Smarties. So yeah, so basically you can eat this. It's algae. So what it does, it's you can see it here. So it takes sunlight. It uses carbon dioxide. So it uses the breath which we exhaust or which we exhale. Sorry, it needs some water as well, and it then produces oxygen, and you can eat the algae. It tastes like, it doesn't taste good, but definitely it's a solution because sunlight is in space available. Carbon dioxide is something which for us is more like a waste product, and then you can grow food and you can get your oxygen. So it's really nice, and it grows very well in space as well. We did an experiment on the ISS, which you can see here. We flew on a SpaceX rocket, which is always nice, and then we grew algae in space, and now we're scaling up our projects to actually try to harvest the oxygen. The first experiment was just to grow the algae and see that the concentration of oxygen was increasing. Now we also want to take away the oxygen and feed it to the astronauts, basically. So that's a bit life support, whereas, as I try to explain you, we were trying to support the astronaut in many ways possible. These are usually relatively small projects with 2, 3, 4 people, but very fun to work on because you can do the whole thing, and it's typically always a one-off. It's always some scientist which thinks about a crazy idea, and then we build it and we test it, and then we fly it. And to close my presentation, I just have some highlights of the things we're doing right now. So as you might know, the Kinetic UK site on the space site has built ion propulsion. Ion propulsion is a way, it's sometimes called electric propulsion, but it's basically a way to have an extremely high speed of the particles which you eject, much higher than a classical chemical engine. And because the impulse which you give to your satellite is the size is basically directly proportional to the speed in which you throw away the particles on the other side, you basically have a very high specific impulse of your rocket engine. The main problem with this rocket engine is that it can only use very little fuel at the same time. So if you compare it, the force is about the weight of 3 euro coins. Probably you have coins in the UK as well, so it's about the same size. So it's not a lot of thrust, but you can do it continuously. And it's a bit the story about the tortoise, if I pronounce it well, and the hare, where you don't need to do a sprint very fast. If you can keep going and keep accelerating at a certain pace, then electric propulsion is the way to cross very long distances in a very efficient time frame, and with very little fuel. And this one is currently on its way to BP Colombo. So BP Colombo is the mission, and it's on its way to Mercury. So the propulsive engine is currently running since I I think more than a year or so. I don't remember exactly when it was launched. We do sometimes also some nice things like this is a Mars sample return. It's a joint ESA-NASA mission where they actually want to bring samples back from the NASA from the Mars soil and investigate it on the Earth. It goes a bit like this. You basically send a satellite in space, or a probe in this case. You let it land on Mars. Then you have another satellite which goes to Mars, which goes into orbit around Mars, and then the one on the bottom will get soil samples, either from robots which are already there, or it just takes samples which are very close by. It puts these samples into like a canister, and then it launches the canister back into space. And then you see here on the right, at some point the soil has to be going from the launch vehicle, which launched from Mars, into an orbiter which needs to return to the Earth. And Kinetic is responsible for this little box here. It's actually a ball basically, but since the soil needs to be inside and needs to be protected from the environment, we need to do explosive welding, and that's what we're trying to prove. It's just a technology demonstration for now, but hopefully we can at some point be part of this Mars sample return mission. We do something with asteroids as well. We're not gonna save the planet, but at least we're going to rehearse it. So the overall idea is that you can buy a T-shirt, by the way, on ESA website. I think this is really nice quote. So the story about asteroids, I think everybody more or less knows what it is about. So you have Mars and you have Jupiter, and in between Mars and Jupiter, you have like millions and millions of pieces of rock, and they're floating away around the sun, orbiting nicely without disturbing too many other planets. But occasionally, these pieces of rock collide with each other, and then they're basically catapulted into all kinds of directions, and amongst others also the Earth. And then you see some kind of diagram here where you see all the astronauts that you know, and then sometimes it intercepts with the Earth. And if you have that, it's actually not a nice sight. Some people think, a falling star, I should do a wish. You should better wish that it's not a big asteroid, because otherwise this could be your last wish. So it is current. This is a 2013 footage from an asteroid of about, I think it's 15 meters, entering the atmosphere in the Ural, Chelyabinsk. It's about 10 times the Hiroshima explosion. Luckily, the explosion is about 80 kilometers above the Earth, but you can't imagine what this would do if it would happen above London or New York or a city like that. There were 2,000 people injured from that incident. Nobody died, but this is the Ural. There's very little people living there. So what are we trying to do? It's a mission where we do an ESA-NASA cooperation. Kinetic is part of the ESA mission, of course. What do? We launch a rocket with our satellite in, and we are launching towards an asteroid called Didymos. Didymos is an asteroid which is more or less on a collision course with the Earth, but we know that in the next thousands and thousands of years, it will not actually collide with the Earth. So it's a safe astronaut to rehearse on, let's put it like that. So we're going to fly to this asteroid. Once we arrive, we will see that it's actually not one, but two asteroids. There's a small one and a big one. We will mainly focus on the small one. And we will try to map that small one as much as we can. So we were interested in the size, in the weight, in the interior structure. So we're going to put a lander there. We're going to measure how things are on the inside to characterize this asteroid as good as we can. We're going to also deploy a couple of CubeSats. CubeSats are new kinds of satellites. They are 10 by 10 by 10 centimeters, but you can stack them onto each other. So this is 30 by 10 by 10. It's a standard size. You can buy standard equipment. It's commercially it's quite attractive. Usually, however, they're built with very commercial components, which do not perform so well in a space environment where you have a lot of radiation from the sun. But for some specific aspects or very short durations of missions, this is actually a very nice technology. Our idea is to then move away from the asteroid once we characterize it, because at the same time when we launched, more or less, a NASA mission launched, which is called DART. And DART will not, like Europeans do, watch from a distance. No, DART will be going the American way and hit it just very, very hard. And the idea is to test kinetic impact. So we want to see what is the change of the orbit of the asteroid before and after the impact. And the main thing is to understand how many of the energy do we lose with heat, with creating the crater, with dust which is moving in all kinds of directions. So it's that kind of exercise. The downside of this mission was that we, at some point, the European side was blocked by budgetary problems, which are now solved. But basically, we are now building the satellite. Also in QinetiQ Space, we're building, let's say, half of it, together with a company from Germany who was building the other half. But the DART one has already been launched. So the Americans didn't wait for us. So we will go after the crater has been created and characterize the orbit and the crater after the impact, which is a bit of a, it's not so nice, but okay, it's what it is. And then the last mission, and then I'll shut up, I'll promise, is a mission which I'm currently working on myself. It's called Proba3. Proba3 is a very special mission. It's about taking photographs of the corona of the sun. The corona of the sun is a bit like the atmosphere of the sun. It's very bright. But to actually see it, you need to block the sun itself, because the sun is a lot more brighter than its atmosphere. So you need to block that disk of the sun in order to see the corona. In order to do that, there are natural ways. In this case, for example, this is the moon just flying in front of the sun. This is really nice that the moon does that. But it only happens about once a year and always in a different area. And sometimes there's bad weather. So there must be a better way to observe this. So the idea would be to put a fake moon in space and then to fly a satellite behind it, which then orbits or takes photographs of the corona. So if you would compare it to this picture, the satellite would be the Earth. The other satellite would be the moon, and then the two satellites need to be put together at an exact distance, both in distance-wise, but also attitude-wise. They need to be perfectly aligned. And then the ball-shaped satellite is actually with a disk. It's not really fully a ball. Will cover the sunlight of the sun disk, and then we can see the corona. There was a movie made about this. Basically, the story is that you need a 150-meter long camera, which you can't launch. So instead of launching one satellite of 150 meters, we launch two satellites. A small one, this is our occulter disk, and this is then the bigger satellite, which is our Coronagraph. And as you can see here, the occulter one will fly just in between the two. It's a very, very challenging, technically challenging project. We have lasers shooting up and down to measure the distance. We have visual-based navigation to get the attitude right. We have to be accurate to about, I think, 1 millimeter at a 150 millimeter distance. So it's very, very challenging to do that. But it's nice because we are a precursor. Now we're watching the corona, but in fact, the technology which we're trying to demonstrate in space is not to watch the corona. It's only for Proba3 that scientists want to watch the corona. The same kind of technology where you block the light of a star is going to be used to observe exoplanets. So now we cannot really see the light of planets which are orbiting another star because the star itself is too bright and the planets are very close to this star. So if we can find a way to block the star, but only the star, then we can actually see those planets. This is actually an observation with a telescope from the ground, where you see 4 planets orbiting a different star. This is not our star. This is another star. I don't know which one it is, but this is how you can basically cover the star, and then you can see the brightness of the planets. Of course, the planets themselves don't shine. The planets are passive, but they reflect the light from their sun, and because they reflect light from their sun, we can actually see them from here. But the idea, of course, would be to do that in a much better way. To be able to do that, you need something like the following, where ideally you use something like a James Webb telescope, which would be then the piece on your right, or the Hubble for that matter, which is a very, 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 very good telescope. And we use a corona disk, which is looking a bit like a flower. I still have to understand why it has these flower-shaped forms, but there's probably a reason for refraction or something like that for the light. And the idea is to launch it together, but then to put them about 1 million or even 2 million kilometers apart, such that the flower only covers one star. And if you cover that one star, then you can see the planets. And if you can see the planets, you can check the wavelengths. You can see whether there's water, whether there's methane, whether there's something which would explain that there is life. So our Proba 3 mission, although it's currently only looking at the sun, it is a precursor for much bigger missions, which are basically waiting for us to demonstrate this in orbit. And it's nice to be part of such a mission. That was my talk. I went a bit over time. My apologies for that. As I told you, we have a massive growth of the company right now. So if you know any kind of space engineers, electronics engineers, which would be willing to move to Belgium or would be just dying to do a job in space, have a look at our vacancies, kineticspace.talentfinder.be, or drop me an email or send an email to the people organizing this session and get me your CV. We need electronics people, we need system engineers, we need project managers, we need test engineers, we need all kinds of people. So if you want to work in space, then think about us. That was it. Thank you very much.
Stijn, that was an amazing trip through space. I think, you know, we've been everywhere, from French Guiana to Mars. What more could we ask? Thank you so much. I hope everyone who's been online has enjoyed it. I think it's been really interesting to hear about so many different aspects of space. And Stijn, on behalf of the branch, I'd like to say a big thank you for the time you've obviously put into what has been a very slick presentation. So thank you very much.
Thank you for inviting me, and thank you for your attention. So